Hi, it's Mr. Anderson, and in this video I'm going to talk about logistic growth. You should probably watch my video on exponential growth if you haven't done so first. But logistic growth is what happens after. In other words, after a population eventually maybe crashes or finds a natural kind of a carrying capacity. And so let's start by talking about population growth in general. Imagine we have 2 rabbits. Our n value is 2. So n is always going to refer to the population size. Now it's going to change over time, but to start, let's say n is equal to 2. R is going to tell us how fast that population is going to change, and we call that growth rate. It really is determined by 2 things, births and deaths. And let's say that these rabbits have 2 baby rabbits. And so we'd have 2 births minus 0 deaths. So that's going to be 2 minus 0 or 2. And then we divide it by our original n, which was 2. And so it's going to be 2 over 2 or 1. And if you have a growth rate of 1, things are going to go really, really quickly. But we could have had a growth rate of 0.5. How could we get that? Let's say 2 rabbits are born, minus 1 dies, so that would be 2 minus 1 or 1 over 2, and that's going to be 0.5. The take-home message about exponential growth, remember, is if r is ever greater than 0, we're going to show fast exponential growth. And so let's say it's 1. What's going to happen? Well, those 4 rabbits are going to become 8. And then we're going to take 8, in this case, times that growth rate of 1. And so we're going to now have 16. And now we're going to have 32, and now we're going to have 64, and we're going to have 128, and we're going to have 256. And pretty soon, my whole screen is going to be filled with rabbits. And I heard my fan come on my computer because it's really taxing to put that many rabbits on the screen. And so does that occur in nature? No. And Darwin noted that as well. He looked at, instead of rabbits, elephants. Elephants take a long time to reproduce. In other words, they have to be 30 before they can reproduce, and they live till they're about 90. And what he found is that even though they might produce 3 pair of offspring during that period of time, if you just let them keep breeding over and over and over again, after 5 centuries or 500 years later, you're going to have 15 million elephants. And so exponential growth goes really, really quickly. And we know that it can't last forever. Eventually, we're going to hit a limit. And so let's look at those 4 rabbits again. Eventually, they're going to reach what's called K, or carrying capacity. It's the maximum amount in a population that it can be supported in a general kind of in an ecosystem or in an area. And so why is that? Well, rabbits eat things, and that is grass. And when they run out of grass, they die. Now, I don't have the ratio right. You have to have way more producers than you're going to have consumers. And so let's put our rabbits on the grass. What are they going to do? They're going to eat the grass, and as they do so, that grass is going to go away, and they're going to have to move on to another area. And so luckily there's more grass for them to find. But eventually they'll eat their way into a corner. And so this rabbit right here has a problem. If this grass didn't grow back, it would really be stuck. And so if we had much more than 4 rabbits, we would have exceeded the carrying capacity. And in class, I asked my students to build models that showed logistic growth. And a lot of them used paper and pencil, but one creative group used Minecraft. And what they did is they constructed a little chamber here, and they put 1 chicken in it. And every time the chicken would step on one of these platforms, 2 doors would open up and 2 more chickens would come out. So pretty soon we had 3 chickens. And they'd step on platforms, and pretty soon we had 5 chickens, and it just went really, really, really quickly. Pretty soon there were chickens everywhere. And I asked them, well, it's got to show logistic growth. And these bright students, Gabe, Ethan, and David, said, well, watch what happens. Eventually, as they stand on the platforms, it becomes so crowded they can't get off anymore. And so they can't release any more chickens into the area, and so eventually it reaches kind of a carrying capacity of chickens in this one container. Now let me show you another model. This is a NetLogo model called Rabbits, Grass, and Weeds. So let me launch that for a second. So in this model, the rabbits are going to be these little white things with ears, and then the grass are going to be these little green squares. And so we start with 5. Now the rabbits are going to find grass if they can, and if they can, they're going to get energy, and if they get enough energy, they can breed. But if they don't find enough grass, then they're going to die. And so if we let it go for a second, it goes really, really quickly. So let me stop it there for a second. So let's watch what happened. And so this red line here is going to represent the number of rabbits over time. And so again, we started with 5, and pretty soon we had 350 rabbits. What happened to the grass? Well, the grass started to reproduce as well, but it crashed because the rabbits were eating all the grass. And so let's watch what happens now if we let it roll for a second. So we're going to see a big drop in the number of rabbits, and then it's going to finally hit a limit. So we're going to find like a perfect amount of rabbits that we have. So we're reaching what's called carrying capacity. And you can see that if we let it go over and over and over, the grass and the rabbits are going to go up and down, but we're going to reach a limit. Now let's say that we gave the grass more energy. So if there's more energy in the grass, let's increase that. We're going to see exponential growth again, and then we're going to have even more rabbits. Or let's say we said that the grass has less energy. As we decrease that, then we're going to have way fewer rabbits. And so that rabbit population is going to drop, but it's going to find another carrying capacity. And so what happens as your population size increases? You run up against these limiting factors, and those limiting factors are going to slow your growth. So let me quit that. So let's get to the math now. So if we're looking at exponential growth, the equation is going to be this right here. And so dn over dt means the change in n over the change in time. And so it's going to be r times n, where r is the growth rate and n is the population size. And so if we started like we did at the beginning with exponential growth, you're going to have 2 rabbits. What's our change in n over change in t? It's going to be 2. How did we get that? We're multiplying r, which is 1, remember, times n, which is 2, and I'm going to get 2. What happens to that change in n? Well, that's going to give me my new population. So I'm taking 2 here plus 2 here, and now I have 4. What's my change in n over time for the next one? Again, since our r is 1, it's going to be 4 again. And so we're going to have 8, we're going to have 16, we're going to have 32. So if we were to graph that, that's going to give us that J-shaped curve. But what I want you to do is look at this equation right here and watch as I change it to an equation that shows carrying capacity. And so the only thing that's going to change is what's in the parentheses right here. And so that's going to be the factor that's related to carrying capacity. And so I'm going to choose an arbitrary carrying capacity. Let's say it's 10, that the area can only support 10 rabbits. Let's watch what happens. And so we start with 2 rabbits. And so I'm going to show you what's in the parentheses here. And so we're going to have k minus n divided by k. Well, what's k? What's our carrying capacity? That's 10. Minus n, so that's minus 2. So we're going to have 8. And then what's our carrying capacity? It's 10. So it's going to be 8 divided by 10, or it's going to be 0.8. Okay, now we're going to figure out this. And so what's this? It's r, which we said was 1, times n, which we said was 2, times what's in this parentheses, which is 0.8. And so that's going to be 1.6. And so this whole equation tells us how many new rabbits we're going to add. And I'm not going to round, so I can show you what happens as we increase this. But know this, that we're going to increase it by 1.6 rabbits. So let's look at time 1. Now we have 3.6 rabbits. Where did I get that? It's the 2 original rabbits we had plus the 1.6. Okay, what's going to be in the parentheses now? It's going to be k, which is 10, minus 3.6, so that's 6.4 divided by 10. Now it's 0.64. You can see that that number became a smaller number. We're going to multiply that times 3.6. Again, it's 1 times 3.6 times that value, and we get 2.3. I'm going to add that to our original 3.6, and now we get 5.9. What's going to be our k minus n over k? It's going to be 0.41. And so what do we get? 2.4. And so you can see that as the population is increasing, this factor is becoming smaller and smaller and smaller. And so now we're only adding 1.4, and now we're only adding 0.29, and now we're only adding 0.009. And so what's happening to n, you can see that it's increasing quickly right away, but the closer we get to that carrying capacity, it's kind of leveling off, and it's reaching that limit at that one point. So this is just mathematical, it's not a model, but it shows that we're eventually going to approach that point. And so again, in review, what's r? R is going to be the growth rate. What's k? K is going to be the carrying capacity. So if our r is ever greater than 0, remember we're going to show exponential growth. And if we ever have k, if we ever have a carrying capacity, we're going to show logistic growth. But we also have species that specialize in these two. We've got R selected species and K selected species. So what does that mean? An R selected species is going to be a species that loves to grow as quickly as it can. Look how many babies this frog is going to have. Thousands of those. And so if I were to take this frog and introduce it into a pond where there are no frogs, we're going to have a bunch of frogs really, really quickly. We're going to have an R that's really, really large, and they're going to fill that area. They're going to run out of resources and crash, and they're going to boom and bust, but they're going to fill it really, really quickly. If we were to look at this, which is a chameleon's going to only have 2 offspring, so its growth rate is going to be really, really slow. What is it going to do? It's going to give them a lot of parental care. It's going to invest a lot of energy in just its few offspring, and they're all going to survive. If we look up here with our selected species, most of those are going to die eventually. But with this chameleon, since it's taking so much care of them, it's going to take very good care of it, and they're all going to survive. This is going to gradually increase and find a nice carrying capacity. So what are we? What are humans? Well, we invest a lot in our young. A lot of my students are 17 years old and they still live at home. Their parents take care of them. So we're really investing in them. So what kind of a population curve are we going to see in humans? We're going to see a gradual exponential increase and then a nice carrying capacity, which we're eventually going to reach. And we don't want to have this boom and bust cycle. So it's not so cut and dry as that. There are obviously species that are somewhere in the middle. So what about a tree, do you think? A tree grows really slow, but they're going to produce a lot of offspring. And so what are they? There's probably no right answer for that. And so again, what is logistic growth? It's growing quickly, but eventually reaching a carrying capacity. And that's based on limits in your environment. And I hope that was helpful.